Let's take a closer look at how we can measure the enthalpy change for a reaction. We do this using something that you're already familiar with from freshman chemistry called calorimetry. The simplest calorimeter that you're familiar with is the coffee cup calorimeter. The coffee cup calorimeter has a nearly adiabatic boundary, which is the styrofoam coffee cup, between the system and surroundings and the rest of the universe. The solution inside the coffee cup calorimeter is both the system and the surroundings. In this case, our system is the reacting molecules in the solution, and the surroundings are the solvent molecules in the solution. Notice that there is no boundary between the system and the surroundings. Rather, the system is dispersed within the surroundings. We typically perform these experiments at constant pressure, so we have a loosely fitting lid, which allows atmospheric pressure to equalize between the outside and the inside of the coffee cup calorimeter. Recall that when we do this experiment at constant pressure, that the heat evolved is equal to delta H for the system. When the reacting molecules or our system undergoes reaction, they will either give off energy or require energy for that reaction to occur. The energy that the reacting molecules give off or take in goes to the surroundings, the solvent molecules. And so the energy that is picked up by the solvent molecules as heat is equal and opposite to the amount of energy as heat given off or taken in by the reaction. Recall that delta H is equal to the constant pressure heat capacity times the change in temperature. If we know the constant pressure heat capacity of the solution, or the surroundings, then we can calculate the amount of heat taken in or given off by these surroundings or solvent. So we can write that delta H of reaction is equal to minus the constant pressure heat capacity of the solvent times delta T. Notice that we are measuring the change in temperature. We know the constant pressure heat capacity of the solvent, and that allows us to calculate from experimental data the delta H of reaction. This argument should be familiar to you from freshman chemistry. What you need to recognize is that in this reaction system, not only are the surroundings increasing in temperature, but since the reaction is happening within those surroundings, it's also increasing in temperature. We're actually making the assumption that the reacting molecules are reacting at a constant temperature, even though they increase in temperature slightly. And this is because the change in temperature is usually quite small, and so we can say that we have measured the delta H of reaction for an average temperature within that small temperature range. A more sophisticated experiment is typically used to do high precision measurements of delta H of reaction. Pictured here is a research grade calorimeter. In this apparatus, the entire reacting solution is kept at a constant temperature by immersing it in a constant temperature bath. In order to measure the amount of energy given off or taken in by the reaction, the amount of energy required to keep the bath at a constant temperature is measured.